Everyone, my name is Vamsi Krishna Bunga and I'll be explaining question 10 of homework 8 of probability and stochastic process course. So let's read the question. The question asks us to show that if the normal process is wide sense stationary, then it is strict sense stationary. So we have a normal process which is wide sense stationary, and we have to prove it that it is also strict sense stationary. So let's go to the solution. Let's first see what is wide sense stationary and strict sense stationary. For a wide sense stationary process, let's say x of t, the expectation of x of t is a constant, and the autocorrelation of t1, t2 is autocorrelation of their time difference t1 minus t2. Now for a strict sense stationary process, the statistics are not affected by a shift on the time axis. So we can write for the density function fx, x1, x2, so on till xn, and time t1, t2, so on tn is equal to fx of x1, x2, xn with a small shift in time epsilon, t1 plus epsilon, t2 plus epsilon, and so on tn plus epsilon. So if this condition is satisfied for any value of n, any value of ti, that is t1, t2, t3, and any value of epsilon, then it is a strict sense stationary. So this is what I meant by the statistics are not affected by a shift on time axis, because t1 plus epsilon, it's still the same. So for the given question, it is given that x of t is a normal process. So we can write the mass density function fx, x1, x2, so on xn, t1, t2, so on tn is equal to 1 by root 2 pi whole power n into square root of det c times e power by 2 into x minus eta transpose c inverse x minus eta, where here c is nothing but autocovariance, and it is expressed as expectation of x minus eta transpose into x minus eta, where eta is the mean of the mean of process x. And let's expand this term. We can write x minus eta transpose as x of t1 minus the mean is nothing but expectation of x of t1. So we can write this term as x of t1 minus expectation of x of t1, x of t2 minus expectation of x of t2, and so on until x of tn minus expectation of x of tn, and multiplied by the same matrix but in the transposed form of it. So it's the same thing, x of t1 minus expectation of x of t1, etc., etc. And since x of t is a wide sense stationary, we know that the expectation of x of t is a constant. So for all these values, we can say it is a constant eta. And if we multiply these terms, these matrices, the output will be in the form, the final form would be like r of t1 t1, r of t1 t2, r of t1 t1 minus eta square, r of t1 t2 minus eta square, and so on until r of to correlation of t1 tn minus eta square. And if we go down, the second row will be r of t2 t1 minus eta square, and so on t2 tn minus eta square, so and so on. It is r of tn minus eta square, so on r of tn t1 eta square, and r of tn comma tn minus eta square. So we can write, since t1 with this r of 0, and all the other terms will be difference in the time axis, therefore it will be t1 minus t1 0, t1 minus t2, t1 minus tn, and so on. It will be t1 minus tn, and so on. Since it is tn and tn, it will be r of 0. So we can write this as c of t1 minus t2, t1 minus t3, and so on, tn minus 1, tn. This can be expressed as c of ti minus tj for all positive integers of I and j. And we can write the probability density function fx x1, x2, x3, so on xn, t1, t2, t3, so on tn as probability density function fx x1, x2, and so on xn ti minus tj for all ij belonging to positive numbers 1 to n. Now let's consider a time shift of small epsilon for all t. So we will write the same thing, but except here it will be t1 plus epsilon, t2 plus epsilon, t3 plus epsilon, etc. And the right hand term will be t1 plus epsilon minus tj plus epsilon. However, these two terms, we can see the epsilon will be cancelled and we get the same expression as this. From here we can say fx of x1, x2, so on xn, t1 plus epsilon, t2 plus epsilon, t3, tn plus epsilon is basically the same as without the time shift. Therefore, we can say x of t is a strict sense stationary process. Thank you.